Cosmology is a big subject, and it seeks to answer some very fundamental questions about the nature of the universe, and it gives important perspective on our place in it. The early universe passed through a hot phase in which it was dense enough that nuclear reactions could go on. That is called Big Bang nucleosynthesis, and occurred in just the first 3 minutes that the universe was around, and basically established the fundamental pattern of elemental abundances, and that is that most of the universe is made of hydrogen and helium, and that's what the sun is and most stars are, and everything else that chemists are interested in the periodic table is just sort of a sprinkling on top of that. And indeed, most of those other elements were made inside of stars later on. It only jives with the abundances that we observe in stars and intergalactic gas clouds if things work exactly as we expected them to in those first few minutes, and that requires two rather different bits of physics. One is that the universe is expanding at that time as Einstein understood, and that you can also derive from basic thermodynamics. It's hot as it expands, it cools adiabatically, and so at some point you get to the right density and temperature for nuclear reactions to go on, which is the other bit of physics we have to understand, those nuclear reactions. On the one hand, I think those aspects of the Big Bang cosmology are very well established. But as we move forward in the later part of the 20th century and on into this century, there are puzzles that come up, and we have had to sort of invoke some tooth fairies to keep things sensible. One of those is dark matter. When we apply the laws of gravity as we understand them to individual galaxies, clusters of galaxies, and the universe as a whole, things don't quite work out. We have made up this story that there is dark matter, there is extra mass there that we cannot see, but which suffices to explain all these different observations. The caveat, though, is that in inferring dark matter, we are assuming the normal law of gravity holds. And the only test of gravity we have on these scales is the systems that don't behave right. So it seems like a very sound assumption that Einstein taught us everything we need to know. And if that is true, then we absolutely have to have dark matter. But one could also take the opposite attitude, that the need to invoke dark matter in these systems is a hint that, Einstein did not teach us everything we need to know, and there might be something else going on. So, MON is a specific hypothesis for how the force law changes at a particular physical scale that is not part of Einstein's theory or Newton's. So in Newtonian gravity, basically the strength of gravity falls off as the inverse square law. Of course, is Newton's famous universal law of gravity. That is why we infer dark matter. That inverse square law doesn't give you enough gravity to explain the observations, given the amount of luminous matter we see. So the other idea is, okay, change the equation. And that is what people generically mean when they talk about modified gravity, and there can be many specific examples of how you would do that. Look at the solar system, where gravity as we know it is extraordinarily well tested and has to be just as Einstein taught us. And then you look at galaxies where things don't work out so well. And indeed, people tried this in the early days when the dark matter problem really, became clear. And that does not work. You can write down equations that change the force law on some scale greater than, say, kiloparsecs on large scale, that you wouldn't notice the change in the solar system, but you would in galaxies. And that just doesn't work for a whole variety of reasons. In galaxies, the place where the discrepancy occurs, that is, in the inner parts of galaxies, what you see is pretty much what you get. The stars suffice to explain the motions. It's not until you get far out in the outskirts of galaxies that you start to notice the dark matter problem. But there is no specific distance at which the problem sets in. Some galaxies, you don't need any dark matter until you're way, way far out. Others, you need it almost right away, never instantly from the get-go, but pretty close. And so it's just a mess. There is no one scale where the problem occurs. The point I'm making here is that if it were a universal thing, it should always occur at the same length scale and not differ from galaxy to galaxy. There's a dark matter problem. We all agree there's a dark matter problem. When things go wrong, you have to bear in mind that maybe we got something wrong along the way, or missed something that is important. And if you assume Einstein's gravity, then the mass density of the universe is bigger than that, and so that leads you inevitably to there being something else that's not just modules. Of course, if you drop the assumption that Einstein taught us everything we need to know, then that argument goes along with it. Then we're in a much harder situation of figuring out something even better than Einstein. That's not easy. I mean, supersymmetry is my favorite example. It was a beautiful idea, very compelling. Was basically accepted widely in the 80s as, must be true, basically because it was theoretically compelling and as they like to say, beautiful. It's not there. It's just not. All the predictions that supersymmetry made have failed badly. And the most popular form of dark matter, the WIMP, is a supersymmetric particle. So you only have WIMPs if you have supersymmetry. And so now we've gotten to this weird point where most people seem to have forgotten that you need supersymmetry to even have WIMPs. Now we have WIMPs because we know we need to have this dark matter, but the supersymmetry that is required to make those things exist doesn't work. And it's failed in lots of ways. And the Higgs, for example, you had to have the Higgs particle to have supersymmetry, and so they had such a hard time finding that. I figured, well, maybe that's because there's no supersymmetry. Well, it turns out they detected it finally, of course, and within a few months, all my particle physics colleagues were complaining because the Higgs was too normal. So it turns out that I had been misled as to exactly what the Higgs was. The Higgs was just the last of the standard model particles, so it was something that had to exist in the framework of the standard model, and it does, great. But in order for there to be a sort of a window into supersymmetry, the Higgs had to be non-standard, right? There's a very simple version of the Higgs that appears in the standard model, and if there's supersymmetry beyond that, then various things should be different about the Higgs. It should have split states or something like that. Nope, you don't see that in the LHC data. And the LHC data are, plenty energetic to see anything that the supersymmetry predictions were being made. Another example of this is the dark matter. The WIMPs that I was talking about, these are expected in that context to weigh about 100 GeV. That's about 100 times the mass of a proton. And, it doesn't have to be exactly that, but ballpark, that's what it ought to be. And so if supersymmetry is real, and if these WIMPs are filling the universe, the LHC is operating at energies of 7 TeV, right? It's got tens, hundreds of times enough energy to spontaneously create WIMPs in these collisions. Nope, zero. Hasn't happened. And it has gotten to the point where most honest theorists are uncomfortable when they realize that supersymmetry has serious problems. With the 21 centimeter observations, we've now added a new wrinkle by talking about this milli charge, MEV, dark matter, whatever the heck they're calling it. This is not your traditional dark matter. It is non-standard physics on top of the already non-standard physics that we've forgotten is non-standard just because we're familiar with it. Other people don't want to admit